These are all from the book, so you probably saw these in the homework. In the first case, we just have to make sure the numbers add up, and then we figure out what the element is. So that's got to be 82 and 206. Then we look at the periodic table. 82 is lead. Okay. Numbers have to add up on both sides. Same thing here. 92 plus minus 1 is 91. 254 plus 0 is 254. So that is Pa protactinium. All right, and the last one, the missing symbol there, again, we can just add up the numbers to find it. That's going to be 38 down here. And then on the top, it's got to equal 236. 235 plus 1. So all of these together have to equal 236 also. We've got 90, and we've got 3 neutrons, so that's 3, so that's 93. 236 minus 93 is 43, or 143, so that's 143. Oh, yeah, you're right. I don't know why I put that there. 38 plus 54 is 92, so that should be xenon. Xenon 143 would be that. You just have to make sure all the numbers add up on both sides of the equation. The top numbers, the bottom numbers, to add up on both sides. All right, a half-life question. The half-life for the radioactive decay is 4.5 days. So every 4.5 days, that sample will cut in half. If the activity is 1 microcurie after 27 days, what was it to start with? So that's saying we have to answer a couple questions here. First, how many times did it get cut in half to get to 1? And then what did it have to be to start with to be cut in half that many times? And like I said, there's like equations and stuff you can do this with. I think we can do it easily just counting it out. So how many half-lives is 27 days if it's 4.5 days of half-life? 6. You can just count that out. So 4.5, another plus 4.5, plus 4.5, plus 4.5, plus 4.5. You just keep adding it until you get to 27. So that's 6 half-lives. So in this case, 27 days is 6 half-lives. So that means some amount of sample, some activity got cut in half 6 times and then ended up being 1. So what's cut in half 6 times to be 1? Well, to figure that out, we go backwards and we double it 6 times. So we go 1 to 2 to 4, 8, 16, 32, 64, right? We're doubling it 6 times. So that means if we started with 64 and we went 1, 2, 3, 4, 5, 6 half-lives, we'd be down to 1. That means we must have started with an activity of 64 microcuries. So then after we cut it in half 6 times, we're down to 1. You guys see how that works? Everybody's looking a little confused. Basic idea? Yeah. So you go forwards or backwards, depending on what the question is asking. Either count it up or count it down, doubling or cutting in half. And then the last part of this was just a conversion. If we've got 64 microcuries, what was the initial activity in microbecquerels, this other unit? And the conversion is given right there. So that's 64 microcuries, 3.7 times 10 to the 10th microbecquerels per microcurie. So those things cancel. So I guess you probably would need a calculator for this. 6.4 or 64 times. Yeah, okay, so we'll say 237 times 10 to the 10th microbecquerels, or in more proper scientific notation, that would be 2.37 times 10 to the 12th. Either way. And if you got this one wrong, you got some other number here, but then you converted it properly, you still get the point for that part. Because a conversion is a conversion. All right, so that was quiz 7. Next quiz will be on the organic chemistry stuff that we finish up today and Tuesday. So let's look at that. All right, last time we did this kind of stuff. We looked at the shapes of organic molecules and all that. Looked at some names, practiced naming some different isomers. We're going to continue that today, but we're going to learn another way to write them. So as you saw, we started using pretty much exclusively these condensed structures because we got sick of writing those H's out all the time, everywhere. And that's fine. We do have to be a little bit careful with this because you don't want to go sticking a CH3 on somewhere else where you have too many bonds to a carbon. So that's one drawback of condensed structures is until you're really used to it, you can often have too many bonds per carbon if you don't think about it, what's supposed to be a CH or a CH2 or a CH3. The other way to do it, where you draw out the full Lewis structure, makes it clearer that every carbon has 4 bonds all the time. Unless it says specifically draw this type of structure on a quiz or exam, you're free to draw however you want to draw it as long as it's correct. But what is important is that you can interpret these structures because you'll usually see something other than the standard Lewis structures. So these were the condensed structures, if you recall. The next thing we're going to learn is really the types of structures that are most used by people trying to communicate chemical structures. And these are known as, I call them line structures. I mean, other people do too. It's not just my weird word. But they're also known sometimes as skeletal structures or bond line structures, depending on the book or the people using them. And I'm going to show you a couple, and then we're going to take them apart and figure out how to draw them and how to know what's happening in them. So let's say we have a condensed structure of hexane like this. There's hexane, and we call that a condensed structure. Hexane, of course, has 6 carbons, so we'll number those carbons here just to keep track of them all. A line structure for hexane looks like this. Obviously, a lot less information there, but it was a lot faster to draw. So let's look at what might be going on here. Well, for one thing, you can see that it has about the same number of direction changes if we count the ends. And it still kind of gives us a sense of that linear structure. If you recall back to when we were looking at those 3-dimensional structures, we saw that the actual 3-dimensional structure really does have more of a zigzag shape. It's not straight. So that's another advantage of these line structures, is you can a little bit better express that real geometry, that actual zigzag geometry that you'd see in a chain. Let's look at another one. Here's an isomer of hexane, 2-methylpentane. And here's how we might draw that in a line structure. So before we talk about the official rules or anything like that, I want you to just take a look at those structures. Take a look at the condensed structures versus the line structures. And just kind of think about them. Think about how you might make connections between them, and then I'll ask you what you found.
I have a question. Mm-hmm. What about this CX second one? Does it have to have somewhere a double bond?
This one?
Uh-huh.
No, it's got its 4 bonds. 1 going to this carbon, 1 going to this carbon, 1 going to this carbon, and then 1 to the hydrogen.
Uh-huh. Okay.
So that's its 4 bonds. Think about those 2 structures. All right, so what do you see? What if I were to draw, let's say, another structure and say, okay, draw the line structure, what would you do? How do you think about this? What's being abbreviated in this line structure?
Basically, it's drawn without the hydrogens.
So it's drawn without the hydrogens. That's kind of the most important part. We don't have to draw the hydrogens at all. What about the carbons? Yeah, the carbons are kind of expressed by where the lines come together, where there's kind of a change in direction or an end. So they're there, but we don't have to write the letters. How do you think we could figure out the hydrogens if they're not drawn like that?
Well, each carbon has 4 bonds, so.
Yeah, so that's why these line structures work. We know that carbon always has to have 4 bonds. So whatever things aren't drawn in a structure like that, we just assume that they're hydrogens. So for instance, if we look just at this one carbon right here, this one is connected to 2 other carbons, here and here. So we can assume that there are also two hydrogens connected to that carbon, because we know it has to have 4 bonds total. And that works for carbons, because carbon always has 4 bonds in these types of examples. So we can make that assumption. Other atoms, other types of things, that might not work so well for. So let's write down a couple quick rules about line structures. So first, in a line structure, we're going to assume there's a carbon atom at each end of a line. And what we call a vertex, which if you haven't heard that term, just means where lines meet together. So like this thing right here. And I think you all kind of saw that when we looked at those two structures. We're assuming that anytime that line changes direction like that, there's a carbon atom there. That means when we draw these line structures, we have to keep that kind of zigzag shape, because if we try to draw line and then line, it's not going to be clear that there's supposed to be a carbon atom in the middle of that. So we keep that zigzag shape. Second, we're going to assume enough hydrogens on each carbon to fill the valence, which we know is just another way of saying 4 bonds. So we assume that there are enough hydrogens on each carbon to fill the valence. That means that, whoops, sorry, back here. If I draw a structure like this, we're going to assume there are 2 hydrogens on that carbon. Everybody see that? It already has 2 connections. So one more. If we look at multiple bonds, now that's changed. Now there's only going to be 1 hydrogen on that carbon, because that carbon has 3 connections already. 1, 2, and then 3. So just by drawing the bonds between the carbons, we can figure out how many hydrogens are going to be on there, because we know carbon always has 4 bonds. And then the third rule all other atoms are not abbreviated including the hydrogen on other atoms. other atoms are not as predictable as carbon in terms of how many bonds they will have. So it's not okay to cut the hydrogens off of things like O or N or other places. We haven't looked at those structures yet very much, but you can have things like this, let's say. So notice that hydrogen is still on the oxygen. We don't cut it off and just say O, because we can't know necessarily that O is going to have an H there or not. So all the other atoms stay the same. If there were an oxygen in the middle of a chain like this, we would leave that there as well. If we had some kind of other atom on there, again, that would stay the same. So those things don't get any kind of abbreviation in these line structures. All right. So now I want to give you two chances to practice here. One, where I'm going to draw a condensed structure and ask you to put it in a line structure. And then one where I'm going to make a line structure and ask you to put it in a condensed structure. All right. So here's my condensed structure. And I know we haven't exactly done this together yet. I want you to try it first, and then we'll look at it together. So there is my condensed structure. It's a pretty big one. But see if you can draw that as a line structure. And then I'm going to draw a line structure and ask you to draw it as a condensed structure. Give it your best shot, and then we'll look at it together. All right, everybody got some ideas? Everyone want to draw what they got up here? Not really? Maybe. Okay, let's look at the technique, kind of how to do this. I looked around, most of them looked really good, so it seems like you have a good feel for this. With drawing a line structure from the condensed structure, there's really nothing to it. You just have to connect things together outside of the carbon atom. So one thing you can do is just redraw the bonds without the carbons in them. You can make kind of a picture like this. You just kind of redraw everything, and then you'd connect them together. The other thing you can do is just draw over the structure itself, connecting the carbon atoms like this, just to kind of give yourself a sense of what that picture is going to look like, and then you can redraw it nicely. So you'd have a double bond here, and then make sure that you don't abbreviate those oxygens. Now, one thing you want to look at in this particular example, right here, you've got two lines kind of coming together. And remember, we always need an angle to show that there's an extra carbon. So when we redraw it, we're going to want to push one of those bonds up a little bit just to make it clear that we're keeping those same angles around. So I'd recopy that, something like this. And see how I'm kind of pushing the angles a little bit so that we can keep that same zigzag pattern the whole way around. So that structure would look something like this. The key with the line structures is make sure all the atoms stay connected to the same things. So all of these need to be still connected to each other. One thing that can help with that is numbering them. 1, 2, 3, 4, all the way around. And then you can say, okay, in this structure, number 1 is connected to number 6. So I got to make sure in my other structure, number 1 is still connected to number 6, because the connectivity has to stay the same. All right, in this example, it's a little bit tougher to go from the line structure to the condensed structure because you have to figure out how many hydrogens are on each carbon. So because of that, what I would do is first just draw the carbons, draw basically the same structure just with carbons. So we'd go C, 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 because we know every point where the lines meet is carbon. So we leave everything else the same and just draw the carbons in like that. Then we can add however many hydrogens we need on each carbon to make sure each carbon has 4 bonds. So how many would I add to the first one on the left there? How many hydrogens does that carbon need? 3. So we'd make that a CH3. What about this one? 2. What about this one? Just 1. That one's just 1. 2. Just 1 here, right? And then 2 here. And 2 here. And if they don't fit nicely next to it, you can put them in front or on top or on the bottom. That doesn't matter. So there's our condensed structure. One thing that can be helpful is to be able to do this. If I asked a question like, what is the molecular formula of this molecule? Now you could count the dots and say, okay, carbon, there's 1, 2, 3, 4, 5, 6, 7. You could count the carbons and then count the hydrogens, but there's a pretty decent chance you're going to miss 1 or 2. I've asked this question a lot, and usually somebody misses a couple because it's easy to miss. If you draw it in a condensed structure and you check your condensed structure and make sure all the carbons have 4 bonds, it's a lot harder to mess up because you see the hydrogens right there. So you can say, all right, let's count them out. Carbons, we have 1, 2, 3, 4, 5, 6, 7, 8. So that's C8. Hydrogens, we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Okay, so that's C8H14. That's the formula. All right. Okay. Now let's look at, for a little bit more practice and some review from before, I'm going to write some names of some compounds, and I want you to draw the compound in a line structure. So let's try this. I'm also going to give you a couple names that we haven't exactly talked about. I want to see if you can figure out what they mean. Maybe that's too tricky, but let's try it. So this is the new thing that we haven't talked about. What do you think 3-chloro means? Yeah, what would you put on carbon number 3 in this structure? Chloride, yeah, Cl. That's all. All right, think about those naming rules, see if you can draw those structures. It might be helpful to just draw the regular Lewis structure or condensed structure first and then put it in a line structure, rather than trying to draw the line structure straight up. That's up to you. I'll give you one more to get those two. Can you get some good line structures yet? So to do these, I see. So one look pretty good. Start with that main name. If it ends with pentane or hexane, that tells you how many carbons to draw. And then you can draw the substituents coming off of the appropriate carbon. All right, in the interest of time, let's take a look at some of these. So for the first one, and I saw some people doing this, this is great, you can just start with some carbons to try to figure out how this structure works out. So the first one is a pentane, so you might just draw 5 carbons in a row. We don't want to fill them with hydrogens yet because we don't know where other stuff is going to go yet. We got 5 carbons in a row, and we can number them. 1, 2, 3, 4. The other part of the name, 3-methyl, tells us that there is a methyl group, 1 carbon, coming off of the 3rd carbon. So we draw that. Now we can fill in the rest of the hydrogens so that every carbon has 4 bonds. Something like that. And then from that, we can draw the line structure. Now, if you have a condensed structure like this that doesn't have the zigzags, the best way to draw the line structure is, again, just count how many carbons there are and draw that many zigzags starting with 1. So we go, remember to start 1 when you put your pen down, not 1 when you make your first line. So you go 1, 2, 3, 4, 5. And then to check yourself, renumber it, because it's easy to add an extra one by accident. So 1, 2, 3, 4, 5. Make sure you actually have the correct number of bonds there, or of atoms there. All right, and then we can just add our methyl group to carbon number 3. And we're set. We're good?
How did you know to put, like, for 1, 2, 3, and then you add the substance?
Substituent, yeah.
Substituent? How did you know to put CH3?
This word methyl tells us that it's a 1 carbon substituent.
Okay.
So that's just 1 C, and then it needs 3 hydrogens to fill the 4 bonds. Methyl means 1 carbon, ethyl means 2 carbons.
Okay.
So we could maybe make a shortcut now for the second one and skip the condensed structure. Now that we know, all right, it's going to be a hexane, we can draw a line structure of a hexane by drawing 6 zigzag thingies. So 1, 2, 3, 4, 5, 6. And then let's number them. 1, 2, 3, 4, 5, 6. So then we've got to add our substituents. The name tells us that there is a chloro on 3 and a methyl on 2. The methyl on 2 is just going to be another line there because that's one carbon at the end of the line. And then number 3, chloro means Cl. So we put a Cl right there. And there's our structure. Now, could you also put the Cl up like this? Yeah, you could. That's still connected in the right way. You'll notice that these bond angles here look really tight. And that's usually why we draw it the other way instead, to kind of spread it out a little bit more. That's more what it would be like in the actual structure. The things would try to be as far away from each other as possible. So that helps it spread out a little bit.
I understand how you draw them and everything, but what are they good for?
What do you mean, what are they good for?
Like, how are they like applied? in the field?
These types of molecules?
Yeah, all those like drawn out structures.
Yeah, well, these types of molecules are going to be the building blocks for everything from polymers and plastics to pharmaceuticals and drugs. So you might start with a molecule like this, do a series of reactions, and be able to build it into a specific molecule that you want. And we're going to look at some of those reactions on Tuesday. But that's the main utility of organic compounds, is the chemistry is really specific and pretty well understood. So you can say, all right, I want to have a chlorine here and an OH over here and 3 carbons over here.
So you can manipulate
And you can manipulate it and make exactly the molecule you want, which then might fit exactly into a protein to stop a disease from occurring or something like that. That's how, well, a lot of viruses are fought that way, but specifically the HIV virus has been modeled, and you can like see the shape of it, and it's proteins that do particular important things for the virus. We know that certain molecules will fit in those proteins and stop it from doing what it wants to do. And so that's how a lot of the anti-retroviral drugs, or the HIV drugs that you take, work, is they have small molecules like this that have been specifically designed to fit in those virus proteins and stop it from reproducing and do what it's supposed to do.
All right, thank you.
So yeah, that's why. And in terms of drawing them, we're still looking at even these up here are still pretty simple small molecules. These things get pretty big, pretty complicated. If you look at structures of, well, yeah, drugs and any of that kind of stuff. So to be able to draw it with lines makes a lot more sense because it's so much faster. If you look at, like, if you have a drug, like a pharmaceutical drug, and it comes with a little drug facts thing, that'll usually have a chemical structure on it, and that chemical structure will usually be drawn in this fashion. It takes up a lot less room. You can make it really small and still legible, all that. All right, so then this last one, 3,4-dimethylhexane. Once again, we draw our hexane. And we put methyl groups at the 3rd and 4th carbons. Something like that. Okay. Another form of alkanes that we want to look at just briefly are the cycloalkanes. These are molecules that have a ring. Cyclo means in a ring. So things like what we drew before. This kind of a molecule has 6 carbons in it. And so we call that cyclohexane instead of just hexane. And this is one of the molecules from lab on Tuesday. It's really important to have that cyclo prefix because that is a totally different molecule from just plain old hexane. Cyclohexane has a formula of C6H12, hexane, regular old hexane, C6H14. And yeah, these molecules are both made of carbon and hydrogen, so they're going to have some similarities. They're both nonpolar and things like that. But they're going to have totally different boiling points, maybe different solubilities of other things, different reactivities. So it's important to keep those things straight. In a name, you just have to make sure that if you see that thing in a ring, that's a cyclohexane. So in this case up here, this would be a cyclopropane because it's got three carbons. You use the same name as we talked about before. You just add cyclo in front of it. Cyclohexane with 6 carbons and cyclopentane with 5 are very, very important because in these structures, the carbon atom can retain its appropriate geometry. And so these are the building blocks for a lot of really important, especially biologically relevant molecules. Things like steroids and hormones are based primarily on this kind of a structure, a bunch of these rings linked together. Okay. So now we're going to get away from the alkanes and go into some different classes of compounds and talk about saturated versus unsaturated compounds. You may have heard these words before, like especially in terms of fats, like saturated fats versus unsaturated fats. And this is what this refers to. Let's take a butane molecule. I'm going to draw it all out here. The formula of this is C4H10. And that's considered a saturated hydrocarbon. What do you think is saturated about it?
That all compounds are connected to a hydrogen, so if it wasn't connected, it would be unsaturated.
Yeah. So in saturated, what we really mean is full of hydrogens, or the most possible hydrogens. The most possible hydrogens per carbon. So you can't put any more hydrogens on that molecule because carbon only has 4 bonds and hydrogen only has 1 bond, so there's nowhere else to connect them. And there's actually a ratio for this. The most possible hydrogens per carbon for any certain number of carbons is twice that number plus 2. So if you have 4 carbons, it is saturated when you have 10 hydrogens. 4 times 2 is 8, plus 2 is 10. So that's the official ratio. If you have 1 carbon, 4 hydrogens, and so on. How do you make it unsaturated then? I mean, we can't just remove the hydrogens because then we wouldn't have 4 bonds on the carbons. So what do we do? Well, let's try it. I'm going to leave this structure mostly the same, but I'm going to take out 2 hydrogens, 1 on each of 2 carbons. We still need those carbons to have 4 bonds, so what else can we do there? Right, we can put a double bond between these 2 carbons. Now that formula, so now carbon still has 4 bonds, everything's good in that structure. That formula is now C4H8 instead of C4H10. And so this would be unsaturated. It does not have the most hydrogens per carbon. And this is exactly what happens with saturated versus unsaturated fats. In saturated fats, they are singly bound long carbon chains full of hydrogens around the outside. Unsaturated fats have some double bonds in them, and so they don't have quite as many hydrogens around. If you've heard of things like omega-3 fats, that kind of thing, the omega-3, omega means the end, and so omega-3 means that there's a double bond 3 carbons from the end. Omega-5 means there's a double bond 5 carbons from the end, and so on. That's where that naming comes from. And those fats are really long chains. They're usually between 12 and 20 carbons. Okay. Another way you can have an unsaturated compound is by connecting it in a ring. because you have to kind of, if you imagine with models, and I didn't have models today, we'll have them upstairs on Tuesday. We spoke about that, but if you imagine you have to pull 2 hydrogens off to get those models to reconnect on the outsides. So if we took a cyclobutane like this, and we put the appropriate number of hydrogens on there, so that there's 4 bonds per carbon, counting those up also gets us C4H8. So that's also unsaturated. In general, multiple bonds and rings make something unsaturated. So if you have doubles or triple bonds in the compound, or if there's some connections in a ring, that's going to lead to an unsaturated compound. So no longer saturated. Questions about that? While we're talking about these multiple bonds, then, let's get into the next category of compounds we're going to look at, which is the alkenes. We'll just start with a simple comparison. This is a molecule we've already seen before. What's the name of this molecule? Anybody remember? Close. Ethane, yeah. So this is an alkane known as ethane. This one is another 2-carbon molecule, but now with a double bond between the carbons, it has 2 fewer hydrogens. And the name of this one is ethene. So as you might see, or as you probably see here, naming alkenes is really not any different from naming alkanes. You just put an E in the end, an E in it instead of an A. So it's ethene instead of ethane. The shape is a little bit different also. Instead of that 3-dimensional tetrahedral shape, alkenes are flat. So that molecule is flat with kind of triangle shape or 120-degree bond angles there. And alkenes are more reactive than alkanes. Alkanes are pretty much only good for burning. They do some other reactions too, but mostly we use them as fuels or as waxes, oils, that kind of stuff where they don't actually react. Alkenes, however, are reactive, and they're used in a lot of starting materials for all kinds of important things. Ethene, for instance, which is also known as ethylene, is a precursor to polyethylene, which is one of our most important plastics. So you might see in some, not pop bottles, but things like milk jugs, plastic bags, all the way up to really high-tech materials, tables and stuff like that. Are made from polyethylene. So the synthesis of that is a really major industry. Just making that particular molecule is a big deal. The tricky part about naming alkanes is there can be one or more of them in a molecule, and you have to name where that alkene is. So let me give you an example. Got 2 structures here. They both have 6 carbons. So they're both hexane, but they both have a double bond. So they're both hexene. As you might imagine, that's not great. That's not an ideal situation because these are obviously different molecules. So we have to determine what the name should be for each molecule. And the way we do that is by numbering the chain. And this time, instead of the substituents having the lowest number, the rule is that the alkene, the double bond, should have the lowest number. So that means we start numbering from this side. In the bottom one, it doesn't matter because the double bond's right in the middle. So it wouldn't matter which way we started numbering it. And we name the compound based on where the double bond starts. In that first compound, that first molecule, the double bond starts at 1. It goes between 1 and 2. So we would call this molecule 1-hexene. The second one, what do you think we're going to call that? Yeah, this one's going to be 3-hexene. Whoops, not hexane, hexene. 3-hexene. So when we have an alkene, we often need to specify where the double bond is. Is it 1-hexene, 2-hexene, or 3-hexene? There's 3 different hexenes that you can have. All right. That's not an issue in something like ethene because there's only one possible place that it could be. It's only when there is that that difference or those multiple possibilities where the double bond could be, you need to make sure to specify it in the name. So let's write that. Another important part of naming alkenes is that the double bond must be a part of the longest chain and have the lowest possible number. Let me show you how that comes up. So let's take a look at this structure. So here we see a chain of 5 carbons going across, and then 1 carbon double bond down below. Because we're used to finding the longest chain, we think, oh, okay, well, the longest chain is 5 carbons. So this is going to be a pentane, and then I'm going to name the substituents from there. But this rule says, no, that's actually not right. The longest chain needs to include that double bond. So the longest chain is actually this one. Even though it's not as long, that becomes our chain that we name. And this other thing here becomes a substituent. So that double bond has to be a part of that main chain. Now we can name that. How many carbons are in that main chain? Yeah, just 4. And that 4 has a double bond at the beginning, so that's going to be 1-butene. And then what kind of a substituent is that? So 1, 2, 3, 4. What kind of a substituent is circled in blue there? How many carbons? 2. So that's an ethyl, and that's connected to carbon number 2. So this becomes 2-ethyl 1-butene. All right, make sure you practice this over the weekend so you get used to some of these names and drawing these structures. And we will come back on Tuesday and finish up the chapter. Please grab your stuff on your way out if you can. Thanks.